Training a large language model is an exercise in software flexibility. You have dynamic control flows, immediate execution, and the ability to debug row by row. But running that trained model efficiently at the silicon level is an entirely different discipline. Deployment requires a systematic abstraction downgrade, stripping away that software flexibility and translating human-readable Python into rigid, static hardware instructions. This process eliminates PyTorch's eager execution mode. Dynamic Python control flows, like if-else statements and variable loops, are frozen into a predetermined mathematical path. The endpoint of this pipeline is a memory-mapped execution provider. This is the transition point where the software environment ends and the physical processor takes over, executing raw tensor math directly on the silicon. Maximizing execution speed requires sacrificing software flexibility to expose the underlying math directly to the hardware. When an AI model runs slowly, the instinct is to blame the computer race. However, in modern AI inference, the physical MAC units calculating the floating point operations are rarely the primary bottleneck. The real friction is physical distance. A neural processing unit relies on two tiers of memory: the extremely fast on-chip SRAM near the compute units, and the much larger, slower off-chip DRAM, the physical RAM sticks located across the motherboard bus. This data shows the bandwidth disparity. On-chip SRAM operates at 19 terabytes per second. Off-chip DRAM operates at 2 terabytes per second. Because of this 10x gap, the computer arrays sit idle, waiting for weights to travel across the bus. This is the memory wall. Every major compiler optimization in AI deployment exists for one specific purpose: to keep data inside the SRAM and avoid touching the DRAM. The first step over the memory wall is freezing the model. Using torch.export, we run a bytecode analysis to capture a purely functional graph, stripping out the Python interpreter and locking the dynamic behaviors into a static path. This static path is exported as an ONNX file. ONNX is not an execution engine. It is a serialized protobuf format, a universal intermediate blueprint of the model's architecture. Inside this blueprint, the structure is rigid. The actual weights, the millions of floating point numbers, are stored as raw, tightly packed bytes within a data structure called TensorProto. During export, PyTorch commands fracture into foundational math. A single nn.linear layer explodes into mapmul and add nodes. The execution provider scans the graph, claiming operations it can accelerate. Unrecognized nodes are rejected, falling back to the CPU and breaking the acceleration sequence. Bridging from PyTorch to ONNX successfully freezes the neural network, laying its mathematical skeleton bare so the hardware compiler can begin its optimizations. Quantization serves as a direct weapon against the DRAM bandwidth bottleneck, allowing more weight data to pass through the memory bus in a single clock cycle. Linear quantization mapping takes a wide 16-bit floating point range and forces it into a dense 8-bit integer space using a scale factor and 0 point. To prevent a single outlier from ruining precision at 4-bit limits, we calculate these parameters per group, isolating every 128 elements. Advanced post-training quantization techniques like AWK and GPTQ map these groups by measuring activation data. They isolate and protect the top 1% of outlier weights to maintain intelligence while aggressively shrinking the rest of the parameters. Inside the ONNX graph, these compressed boundaries are tagged using quantize and dequantize, or QDQ, nodes. These nodes mark the precision boundaries for the hardware. Mathematically, shrinking the data payload allows the NPU to physically transfer more weights per clock cycle from the DRAM into the fast SRAM. When a neural network executes sequentially, each step pays a hardware transfer penalty. A matrix multiplication is computed, written to DRAM, and then read back out for the next operation. Operator fusion collapses sequential ONNX nodes into a single hardware kernel. Compute units execute multiplication, addition, and activation in one continuous SRAM pass. Instead of multiple trips across the memory bus, the fused kernel requires exactly two: one read from DRAM and one write back. This principle scales up to the core of the large language model. Flash attention is an extreme application of operator fusion, applied directly to the query, key, and value calculations. By splitting the matrices into smaller tiles that fit inside the SRAM and calculating softmax probabilities progressively, Flash attention prevents the massive N-by-N attention matrix from ever materializing in the slow HBM. Operator fusion directly increases execution speed by eliminating the physical necessity of writing intermediate math back to slow memory. As an LLM generates text, it builds a history of key and value vectors called the KV cache. Pre-allocating the maximum possible continuous memory sequence for each request results in massive fragmentation, wasting up to 80% of the DRAM capacity. The solution mirrors OS virtual memory paging. An OS routes virtual pages to scattered RAM. Similarly, page detention uses a block table mapping token sequences to non-contiguous physical DRAM on demand. This decoupling lets sequences share prompt prefixes, only duplicating memory if a sequence diverges. Treating AI memory like OS virtual memory reclaims wasted DRAM capacity, significantly boosting the batch size and overall throughput. Generating text step by step is an auto-regressive bottleneck. To output a single word, the system must load the entire multi-gigabyte model from DRAM. This is a massive expenditure of bandwidth for an incredibly small amount of computation. Speculative decoding introduces the draft verify paradigm to bypass this limitation. First, a tiny 1 billion parameter draft model quickly guesses multiple tokens, barely stressing memory bandwidth. Next, the massive 70 billion parameter target model takes over. It loads its weights from DRAM exactly once, scoring all 5 guess tokens in parallel. Because the target model is evaluating an existing sequence rather than generating one step at a time, scoring 5 tokens takes virtually the same time and memory bandwidth as generating one. Through modified rejection sampling, the accepted tokens are mathematically guaranteed to match the probability distribution of the target model. There is zero loss in generation quality. Speculative decoding artificially creates a compute-bound batch process. It trades the NPU's abundant compute cycles to save its scarce memory bandwidth. LLM architecture is constantly evolving. The standard layer norm from 2017 has been largely replaced by RMS norm, and standard ReLU activations have been replaced by SWIG glue gating mechanisms. These changes improve model accuracy, but they create unfamiliar, highly fragmented subgraphs inside the exported ONNX file. If an execution provider lacks a fusion template for a new architecture, it fails to match. The NPU rejects the graph, kicking the operation back to the host CPU. Copying tensors over the slow PCIe bus creates a massive latency penalty, ruining hardware acceleration. High-level architectural innovation is ineffective at the edge if the hardware compiler's pattern matching capabilities haven't evolved to support it. In the realm of deployment, the model's memory layout and available bandwidth dictate performance far more than raw computational flops. This is the physical endpoint of the pipeline. Your high-level code ultimately has to execute on these exposed dies. The AI engineer's core task in deployment is profiling ONNX graphs, verifying custom operator support, and aligning pure mathematics directly with the silicon layout. Quantization, operator fusion, page detention, and speculative decoding function as a unified toolset to bridge the gap between Python scripts and the physical constraints of the memory bus. Scaling true AI performance at the absolute edge requires mastering hardware-software co-design to finally shatter the massive memory wall.